Goal of the ASSURED-UAM project is to deliver comprehensive knowledge for the most promising scenarios in terms of advancements in urban air mobility area. In this manner, 6 use cases were identified and spread over 3 time horizons: 2025, 2030, 2035. In the table we can see the details for each use case which describe the UAS parameters and number of landing pads or vertiports. Within the nearest time horizon, delivery of parcels or medical equipment with the use of multi-rotor drones occurs to be dominant among all UAM operations. With time advancing, new configuration of UAS should enable both heavier cargo delivery missions or personal transportation. Extended flight ranges observed in 2030 and 2035 time horizons are expected to appear due to the foreseen development of battery technologies. In order to describe any product in terms of costs borne during its whole life cycle, the environmental life cycle cost analysis should be performed. As a result, we obtain either total or unit costs of the product as well as their breakdown structure. To carry out such analyses for UAM use cases, the following cost components were identified. Among them, we can distinguish investment costs, energy costs, operating costs, delay and deadhead costs, environmental costs, end-of-life costs. All of them contribute to the total cost with different weight, depending on the assumed parameters of the product, service. As we already know, environmental life cycle cost analysis includes different cost categories. In this slide, you can find out detailed information about each one regarding UAM use cases. Investment costs, aircraft cost, vertiports, building, modernization, software costs, certification costs, energy costs, aircraft flight energy consumption cost, energy consumption by landing pad vertiport infrastructure, operating costs, direct operating costs, indirect operating costs, delay and deadhead costs, delay costs, deadhead costs, environmental costs, CO2 emissions fee during flight, noise pollution costs, end-of-life costs, recycling costs, incineration costs. Investment costs are the initial costs that have to be borne to start the operational phase of the product service. Usually they involve the cost of product, aircraft purchase, costs of construction works, landing pad vertiport, necessary equipment installation, and many more. In principle, these costs are borne at the very beginning of the investment process and typically have the biggest contribution to the total cost. The energy costs for UAM operation relate to the feeding of propulsion system of the aircraft and to the energy consumed by the airport vertiport. Operating costs, on the other hand, are for all costs arising during the operational phase of UAM services. As shown in the charts, the bigger the aircraft, the higher the costs of operation. It is strongly related to amount of energy or work needed to operate both aircraft in the air, but also the operation on the ground. The main division of this category, operating costs, falls into direct and indirect costs. The first one is associated to the costs of operational activities of UAM services, namely flights. The second subcategory refers to the costs that are borne in order to perform the operational activities but are not directly related to flying itself. For sure, not all are applicable for specific business cases, e.g., passenger service related costs with cargo transport. Delays are very common at civil airports due to multiple reasons, such as bad weather conditions, air incidents including bird strikes, air traffic control restrictions, passenger punctuality, cargo loading problems, and many more. It is expected that such delays may also occur to unmanned operations, especially when the number of aircraft airborne will rise. It is clearly demonstrated in use case 3, where multiple parcels are planned to be delivered and which may be prone to multiple delays. Deadhead ratio is the number that represents the empty flights conducted by the aircraft in order to reposition itself. It is often related to the demand for the flight from the airport located in geographical region other than of current position of the aircraft. Usually, the share of empty flights depends on the real demand for provided service, fleet size, and capacity optimization, as well as on quality of resource optimization process. In environmental life cycle costing analysis, environmental costs are treated as an extra information available in the standard LCC life cycle cost analysis. Environmental costs of the UAM operations are expressed as the cost of CO2 emission rates, as well as the noise pollution costs. End-of-life costs, on the other hand, cover recycling, incineration, and landfilling costs. Aerial operations utilizing big aircraft generate more carbon footprint and thus are more susceptible to higher environmental costs, which are visible for use cases involving passenger transportation or multiple packages delivery. Since urban air mobility, also known as UAM, is quite a new approach to traveling, it should be explored in terms of how energy efficient it is. As we know, energy consumption converts into costs of the travel and thus the cost for the individual passenger. Energy efficiency of UAM means is calculated similarly as that of other modes of transportation, such as bus or train. It is energy expressed per one passenger per 1 kilometer, known as PKM. Parameters, which were specified on the chart, allow for the comparison of energy efficiency of UAM passenger transportation with other modes of transport, mostly ground-based. The main conclusion regarding UAM economic aspects are: people transportation by buses, trains, especially during the peak hours, remains more energy efficient than UAS in given use cases. Compared to the electric or hybrid cars, the electric UAS have worse energy efficiency, which is related to the greater amount of energy required to lift the UAS. Although some of the ground transport modes are more efficient than UAS, it's important to remember that utilizing aircraft for people transportation is performed much quicker, 4 to 12 times, and more comfortable, which makes this transportation means more favorable for high priority operations. The topic of the carbon footprint focuses on the impact of UAM on the environment. While in the calculation of environmental costs, the financial aspect was taken into consideration, the calculated data refer to the after effects that UAM will bring in terms of greenhouse gases emissions. To analyze the carbon footprint of the UAM services, it's crucial to underline the fact that not only during the operations, the carbon emissions are released into the atmosphere, but also in the manufacturing and end-of-life phase. The chart shown in the slide compares the environmental impact of all identified use cases in 3 different countries. The total unit carbon emissions of use cases UC1 to UC4 are expressed in kilogram CO2 equivalent per kilogram kilometer, as referred to cargo transportation, whereas use cases UC5 to UC6 are expressed in kilogram CO2 equivalent per kilometer, passenger transportation. The main conclusions from the slide are as follows: the greater contribution of fossil fuels in electricity mix of the country, the greater the carbon footprint. Passenger UAM services with greater MTOW exhibit higher total unit carbon emissions than small cargo drone deliveries.